So today we're going to start. This will be a little bit less polished of a class than other times, but that's okay because I'm not all that polished in the first place. So for viewers at home, I left all of the technology upstairs. So this will be a Blackboard talk. Okay, so what we're talking about today is how do we talk about light? So we're just kind of talking about photons in a meta sense. So the first thing that we need to talk about is this. I'm gonna write this up here again. So the flux is the luminosity divided by 4 pi times the distance squared. So what this says, here, I'll write this here too. So what this says is I've got some source of light, we'll call it a star, because basically everything we're going to deal with for the next little bit is going to be focused on stars. But all of this is true if you're looking at a galaxy or a planet or a black hole. Well, a little not so much black hole, because when you get really close, all this kind of breaks down. But we're never really close to a black hole, so it doesn't matter. So I have a certain amount of light coming off of my star. Let's make it star-shaped. And this light, we're going to call it L, and this is the luminosity. And we measure this in ergs per second, per wavelength, per area, per steradian, per solid angle. Because those are all the things that you need to break up how the frequency that we're going to get. So, so we're going to measure a total amount of energy in ergs per second, and that's going to be spread out in a spectrum, so it's per wavelength, and I'm going to have a certain collector area of my detector, or emitting surface area of my star, so I'll have an area, and then I'll have the amount of the sky that I'm either radiating into or collecting from. So this is a similar kind of thing. So the flux, if I'm at some distance d, the flux that I measure out at this distance d is just going to be the light divided by the surface area of the sphere that the light has been spread out over, which is just 4 pi d squared. 4 pi d squared is just the surface area of a sphere with radius d. So when, oh man, I got good graphics for this lecture too. When Hipparchus went up to try to describe how everything worked in the sky, so luminosities are going to be, sorry, let me back up. Luminosities are going to be the things that we're looking for. So this is the ground truth that we need to determine what a star is. So the luminosity is the thing that we're looking at. The flux is the thing that we can measure. So that's what my telescope tells me. So, so I have 3 things. One is what comes from a telescope, probably. One is what comes from the object itself, and one is the distance between us and the object. They're all unknowns, they're all kind of complicated to get, so we have to work for each one of them. Okay, hang on a second. Let's see, does anybody have any questions about that right now?
So that's force like F equals ma force?
No, this is flux.
Oh, flux, right.
Yeah.
Good thing I asked that.
Yes, that's why I stopped there for a second. So this is flux over luminosity over distance squared. And then there's a 4 pi for geometry.
Why do we denote it with an F and not a phi?
For flux,
Yeah.
because flux starts with F.
Normally we use phi. Like,
Who?
Physics too.
yeah, physics is
Yeah,
used
yeah.
for electric flux.
I use F.
But that's
So-
force.
What's that? I know, yeah, there's not enough letters.
He fears no God.
Is this
Yeah.
the same as the
He's just throwing F's everywhere.
flux, or is this a different
Which,
flux?
that was a good question. So I'm gonna, somebody, maybe you, asked if this is the same flux that's used in Gaussians, and the answer is yes and no. So, no, not really. This is a flux that's in these units.
Pain.
No, it's not that bad. It's just energy per time per geometry.
Okay.
Now, are those SI units can we use per geometry?
Yeah, but you have to expand out what geometry is in CGS. So it works. You just have to then turn the crank and get the rest of it out. So what does the geometry entail? The geometry entails which part of the spectrum you're looking at. It entails how big your star is. It entails how much of the sky your star can see. So those are the important bits. So remember this, then actually go derive this. So this is the flux in terms of photons. So it's like how many photons are crossing a certain area per time. If I'm looking at the Gaussian flux, so when we had, like, when you did E and M, I don't know if you did this in E and M already. So you've got an electric field like this, and you'll have a surface like that, and you'll have a flux of electric fields out of a certain surface. It works exactly the same way for the exact same geometry, but it's a different thing that's on the inside that's spitting out all the stuff. The same kind of equation works if I've got, if I'm looking at for, say, the flux of anything coming out of anything else. So if this Coke bottle explodes, there will be a flux of Coke going everywhere, and that would be measured in Coke per unit geometry, Coke per time per unit geometry. The geometry is all the same, but what's inside is different. But we love, so there's this beautiful thing, integral of grad f equals f at the surface. That's not how you wrote it. You wrote it like two integrals, but I'm writing it this way. This is the same. All of that Gaussian crap that you did before all still works and is all the same because it's core physics. It just comes from geometry. Now, it breaks down when you're near a black hole because geometry doesn't work like that anymore because the space gets all curved and jacked up. So the volume of the surface area of a sphere is not 4 pi times its radius squared. But we're not there yet. So, all right, so Hipparchus, back in the day, so these are the quantities that we care about, but they're not the only units that we're going to use because we're tied to this magnitude system because of history. And that's not on that work. So Hipparchus, when he was alive 3-some-odd thousand years ago, looked up in the sky and said, "Okay, I want to try to catalog what the stars are doing, write down what everything is doing, and make some kind of ordered assessment of what's going on." So he looked up into the sky and he sorted all of the stars into 6 bins. And he sorted them, and the first bin is the brightest things, he called those first magnitude. And then the last bins he called the dimmest things, he called those 6th magnitude. There aren't any 7th magnitudes of stars that you can see with your eyes because your eyes kind of suck. If your eyes were bigger, hawks and owls can see much, much more stars than we can because they have better eyes, they have better night vision than we do. So he did that, and what he wound up doing was setting the stage for an annoying system of units that we use for the rest of our lives. So if I measure the flux in ergs, and I say, okay, this object looks twice as bright as this other object, the flux from the first object is going to be an order of magnitude smaller than the other object. Yeah.
Don't we like take it in? Isn't that just, I mean, can't I say something is twice as bright, you say it might be 3 times as bright?
Well, so I mean, we average over people, but most people are about the same when you say twice as bright. But more importantly, it's all a logarithmic scale, because if I perceive something to be twice as bright, it's a factor of 10 brighter. A lot of human perception works on a logarithmic scale because that gets you a bigger dynamic range. It lets you see tiny things and big things, or bright things and dim things. But it's logarithmic. So we need to turn this flux into a logarithm. So the thing that I want to measure is the log of the flux. And we're actually going to use the log base 10. Now, what is the log of a second? That doesn't make any sense, does it? What is the log of a meter? Also doesn't make any sense as a thing. You can't take the log of units because I don't have a logarithmic. That just doesn't make any sense, right? So I can't put anything in a log that has units on it, right? So I have to. So this is the flux that I measure. I have to normalize it to something so that I can take the log and make it make sense. One of the things that astronomers developed over the last couple hundred years is they realized that if I point my telescope at the thing that I want to point my telescope at, that's my measurement, and then I point it at Vega. Vega's a star, it's an A star. What I can do is measure the brightness of this star, and then using the same sky with the same shit in it, and the same clouds and turbulence and whatever, and my telescope behaving the same way it did today, because it's the same day. I measured two different stars and I measured their relative brightnesses. Does that make sense? So by measuring the relative brightness, I can divide out all of the systematics from my telescope. So it doesn't matter how sensitive my telescope is that particular day. It doesn't matter how bad the weather is. I'm going to get the same relative brightness. So all of our things are developed relative to an A star. And, okay, Hipparchus said that the brightest thing is 1 and the dimmest thing is 6. Why is that a problem?
It's not a very big scale.
It's not a very big scale. That's okay, I've got a log.
Oh.
So the log of what is 6?
1,000,000?
Yeah. Right, so my scale's plenty big, but it goes backwards. Bigger numbers should be more stuff, not less stuff, right? But that's the way he did it. And it turns out that it's about a factor of 5 that you see. So what we wound up deriving through all this complicated business is the magnitude system, which says, okay, the magnitude that I want is going to be relative to my fiducial star is going to be minus 2.5 times the log base 10 of the thing that I want over the same measurement for an A star. Yeah.
What's an A star?
An A star is a kind of star. That's all we need right now. It's a particular temperature of star. We'll get more specific. There's a whole complex spectral classification that I'll get into later, but we'll just call it Vega for now because you can always see Vega.
What's that part right before log 10?
Minus 2.5. Let me rewrite that again. So the apparent magnitude, let's talk about the apparent magnitude. Is M, let's write it the other way. Well, okay, let me do it this way first. M minus M for an A star equals minus 2.5. That's important. Log base 10. Here it's important that you use the log base 10 because otherwise you'll be off by a factor of like 1.7. Of the flux that I care about divided by the flux of an A star. So I have this system where I have two stars. If one of them is a factor of 10 brighter than the other one, then it's a difference of the log comes down and that becomes a 1. It's minus 2.5 different in its magnitude. So a brighter thing has a lower magnitude. The sun has an apparent brightness of minus 26. That's very bright. Vega has a brightness of 1. Wait, does this make sense? This will make less sense as we go on. So this is the apparent brightness. It's what I measure versus what I look up, because we don't actually use Vega, we use this ensemble of a standard magic star that works. And this is the thing that I measure, and this is the thing that I look up. Or calibrate my telescope. I use that to calibrate my telescope. So the magnitude system goes backwards from what we want, but it's a log, and it's useful that it's a logarithmic scale because we have things that vary by many, 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 many orders of magnitude. So the apparent brightness is what I measure relative to an A star. There are several other magnitude-looking things that I'm going to describe that look pretty similar. So the absolute brightness is the brightness as if it were at 10 parsecs. Why 10 parsecs? Somebody thought that was the right thing at some point in time. It doesn't matter at all, but we need some kind of fiducial thing. Because it's a logarithmic scale, and this goes like 1 over d squared. I mean, I can't say d equals 0. That means the flux is infinity, right? So that doesn't make any sense. The thing that we're trying to get our head around is the luminosity. That's the thing that we're trying to get at. And I'll talk more about that in a second, but we need the measurement. We need to talk about the measurement tools too. So the absolute brightness is trying to get at the actual flux. The absolute brightness is the flux as though it were at 10 parsecs. So this is something that depends on only the object. So the apparent brightness is my measurement, and this depends on the object and its distance. The absolute brightness only depends on the distance to the object and what the object is. So now, one thing that I can do.
And for absolute, it doesn't matter what base logarithm you use?
No, you should use 10 always. So with magnitudes, it's always log 10, even if I write ln. Because I'm going to screw up and write the wrong thing. Yeah.
And the 10 parsecs, so is it 10 parsecs squared?
Yeah, written this way, it's 10 parsecs squared. So a better way to write this, let me redo this. I wrote that a little wrong. This should have been a big M. So this is 10 parsecs squared down here. This is 4 pi times 10 parsecs. So the absolute brightness, yeah.
Oh, finish that.
Okay, so the absolute brightness is M. The apparent brightness is little m. And then the flux is, and then on the right-hand side is the flux over at 10 parsecs, yeah.
So shouldn't the right side be positive then?
Not yet. Hang on one second. So I'm gonna get rid of this this square. So this becomes, I'm gonna do a little bit of algebra. And this becomes m minus little m. So that d has a square in it. What do logs do? Brings down exponents. And the d's in the bottom, right? So it's minus. So I get a 2 and a minus sign, which turns my minus 2.5 into a positive 5. Plus log base 10 of the d, of distance in 10 parsecs. This one is not squared. I took 5. So the absolute brightness is defined this way, and we can define the distance modulus as mu equals big M minus little m, which is going to be equal to 5 times the log base 10 of the distance in 10 parsecs. Or you might see this written as 5 times the log base 10 of the distance in parsecs plus 1 minus 1. So how do you use this? What do we actually do to determine something? So we have catalogs of the absolute brightnesses of all of these stars. How do we know that? Well, we've got to know, how do we know what a star is once we know what its brightness is? Well, the easiest thing to do is measure its temperature. Sorry, I'm gathering my thoughts so that I go in the right direction. Yeah, so the next thing we want to do, so we'll come back to fluxes in a second. I'm actually going to write this up over here. So for all of these, I have M1 minus M2 equals minus 2.5 times the log base 10 of flux over the flux of flux 1 over flux 2. So all of these relationships look like this. And you can tell it's got to be the difference of things because I've got the log of the quotient of things. So the apparent brightness, M1 is the apparent brightness. M2 is an A star, and F2 is an A star. The absolute brightness, we have big M minus little m equals minus 2.5 times the log base 10 of the flux over 10 parsecs squared. Is that how I want to write it? That's not how I want to write it. Let's not do it that way. Ignore that. 5 log d over 10 parsecs. Where big M is the absolute brightness, little m is the apparent brightness, and d is the distance. So why does this work? So big M is what the star is doing by itself, and little m is what I measure. Yeah.
And what is an A star? It's just something you measure in reference to?
Yeah, an A star is a kind of star, and I'll explain that in a little bit. And then the distance modulus U equals big M minus little m equals 5 log base 10 of d over 10 parsecs. So what are we gonna try to measure with this? Well, we're gonna try to get our head around spectra.
Are the 10 parsecs a unit, or are you just dividing the distance by 10 parsecs?
B, the second. Both, really. I mean, a lot of times you'll see this as this, where they say D is in units of 10 parsecs, but that's confusing. So I like to throw in the fiducial units whenever I can, just so that it's always clear. So this 10 parsecs is there to get rid of the units, normalize everything. Book. So the thing that we're trying to do is to get the temperature. And to get the temperature, because that's going to really tell us a lot. Temperature is really important. That's the first thing that I ask about before I go outside every day is what's the temperature? Not here, I know it's going to be nasty out, but in other places where there's weather.
Weather, it's just bad weather.
It's actually getting nice right now. I actually like it between about October through June. It's not bad here.
Don't like our 2 seasons of hot and hotter.
Yeah.
Can you read the distance modulus equation? I can't.
Yeah.
Are they not the same?
Was that
Absolute.
they're super related. So the absolute brightness is this part.
Yeah.
The distance modulus is the difference.
Wait,
Okay.
is that M or mu?
This is a mu, this is an m.
Okay.
And this is a 5 log base 10 d over 10 parsecs.
Got it.
Got it.
Doesn't need a true.
What's that?
I'm just talking about a Russian rhyme.
Oh.
I'm sorry. I got distracted.
No worries. Okay, so what we want to do is get the temperature. So all of this is a lot of machinery that'll get more confusing as we go on. But we need to talk about temperature first. And what we're going to talk about actually first is the black body function. Oh, actually first, I want to run through the questions before I get into black body. So, that's why I wanted to talk about the questions. Okay, so that's the first pass over E and B. Let me go over the questions. E and B, magnitudes. E and B is next. So, okay, so the questions from the reading. Let's put a pin in magnitudes. We'll come back to those in a second. Let's talk about the reading. So the reading had this whole section on Poynting flux that I'm not going to go through. That you've read now. I'm not going to test you on any of that, on that whole section. But I'm going to answer your questions. So, so the first question was what are Maxwell's equations and what are they used for? So I'm going to talk about them because they underpin everything, just about everything. So we got two quantities, the electric field and the magnetic field, right? And they're both space-filling vectors. They have 3 components, and they do stuff. We're not going to talk about magnetic fields ever in this class, I don't think, but they're what I spend most of my professional time working with. I spend 0 time on electric fields. So electric fields go away really fast. But magnetic fields, you can make those stick around. So E and B are both vectors. And we have, so to completely define a vector field, it is sufficient to define its divergence and its curl. Does that make sense? So this is like, to define a line, all you need is its slope and its intercept, right? This is the same idea. You just need the derivatives of the field, but you need all of the derivatives, so you need both the curl and the divergence. So we need an equation for the divergence of E, the curl of E. Actually, let's do the divergence of B first. This is always done that way. The divergence of B, the curl of E, and the curl of B. Now, you don't need to know any of this. None of this is going to be on the test, so I'm just going to say this to you. Can feel free to take notes, but I'm not going to ask you about any of this again. So the divergence of E, what does that mean? What is the divergence of E? So the way you think about this is I got a point. E is radiating off of that point. I define some surface. It's how many lines are actually coming off the point. Or it's the net flux of lines through the surface. The divergence of E is rho, the internal charge, over epsilon naught, this constant that we shouldn't have to deal with, but we're stuck with MKS, so we have to. In CGS, that's just 4 pi. The divergence of B is 0, and this is all the way 0, not approximate 0. With the exception of magnetic monopoles that were created at the Big Bang, that may still exist, but I probably don't. The curl of E, why am I looking over there? Is dB dt, and the curl of B is mu naught, another one of these dumb constants, times J, the current, plus 1 over epsilon naught dE dt. Okay, so.
Is that a delta or a partial?
Partial. So Maxwell's equations relate the curl of E and B to the time derivatives of E and B and other things going on. Now, one of the cool things you can do is you can take the time derivative of this one and the space derivative of this one, do a little bit of algebra, and you're left with a wave equation. That wave equation says del squared E minus C squared d squared E dt squared equals 0. You may not recognize this right now, but this is a wave that propagates at the speed c. And if you do the algebra, this c is equal to mu naught epsilon naught, and it is the speed of light. So Maxwell's equations contain the speed of light because equations are photons. No, because photons are light, and photons are electromagnetic. So then E cross B is then the Poynting flux, and that's the actual transport of momentum by the fields itself. The book talks about them, but I don't really need to spend too much more time about them.
J next to
J, yeah, that is the current.
What is under C?
Where? Mu naught epsilon naught. C is equal to mu naught epsilon naught.
Oh, okay.
C squared is equal to mu naught epsilon naught. Let's see. There was something else? Okay, so after this, we don't have to think about them any at all. So come back to E and M. These are the coolest. I love Maxwell's equations. But we don't need them too much right now. But I figured I'd throw them up and talk about them for a second. Okay. Yeah. 8 people said, can you go over the Poynting vectors and why they're useful? They are useful, but I don't need them right now. Okay, does everything have a radiation pressure? All photons have a radiation pressure. So every photon runs into something, and that's just F equals ma again. If a photon runs into something, it got hit by something, so it's got to be a back force. So there has to be a force, so there has to be a change in momentum. Was that? With no mass. So photons have momentum, but not mass. Because F equals ma should really be F equals p dot, because momentum change is really the important thing. What is bolometric correction? Bolometric correction means all of it. Whereas monochromatic means just one. So we've got 2 different kinds of light that we've talked about. Several of you asked what monochromatic means. Monochromatic means exactly one frequency and no other frequencies. Let's see. What are apparent and absolute magnitudes, and what's the difference? So the apparent magnitude is what you measure on the ground, and the absolute magnitude is what you would measure if the star were at 10 parsecs. They're actually very different things. One has to do with how far away the object is. The other has to do with what the object is. So the absolute magnitude tells you what it is, and the apparent magnitude tells you how far away it is. Does that make sense?
Are the words magnitude and brightness used interchangeably?
Yeah, just about. Magnitude is the formal unit, so you can have a magnitude of something. Let's see, distance modulus, UVB, I'll talk about UVB in a second. Does radiant flux behave like electric and magnetic flux? Yes, but different. Does the 10 matter? Yes, the 10 matters in the log, so that's important. Where did Maxwell find the constants that define the speed of light? So this is kind of awesome. So they developed these equations all independently. They're all coursing around with putting stacks of lead and copper together and then putting wires on the end and touching them to frog legs and watching the frog legs jump around. No joke, that was some of the earliest things they did with electricity. It's all right, that's fun things to do, right?
Weird science experiments from early science.
Yeah. Even recent science, when I was in college, somebody at one of the big magnet labs in France levitated a frog in a magnetic field. So they developed these things all independently. They had a thing for electric fields and a thing for magnetic fields and a thing for the changing magnetic fields and a thing for changing electric fields and all of these various equations that Maxwell had the insight to tie everything together and said, oh, there's only one thing going on here. But how the actual process of coming to that was took a long time. What do black bodies radiate? Photons. So the radiation that we're talking about is photon radiation. So the photons coming out, not like nuclear radiation. Let's see. How do you use distance modulus to get the distance to a star? So to get the distance to a star, you need to get the absolute brightness from knowing what the star is. That's kind of hard, but you can do it. And then you get the apparent brightness by just measuring it with your telescope. Then mu is big M minus little m equals 5 log 10 of d. So you just invert it. And you get d equals 10 to the mu over 5. Right? So these two things are related and useful for getting distance, and that's a thing that I'll probably make you do in the homework. UVB. Will we review main sequence stars? I will. What is propagation? Propagation just means moving under its own power. So a photon goes from here to here, it propagates. And the propagation is the moving through space. There's a couple more questions in there that I will get to in a minute after I talk a little bit about black bodies. So, and let's see, I don't have, okay. So, let's talk about the black body. So one of the most useful things that we've ever developed is the understanding of the black body. So let's talk about what it is, and then we'll stop talking. So I'm looking at the distribution of energy, not just energy per second, and then geometry, versus wavelength. So I want to know how much energy I have at various wavelengths in my system. So this is true for any kind of system. This could be an exploding star. It could be a blob of hot gas. Let's talk about just a star for a second. A star or an oven So an oven, let's pretend that's an oven. The light comes out here, right? Is a thing that has a temperature. Now what we want to assume, so there's all of these rules about what makes a black body, but really the important thing is all you're seeing are the photons coming out because it has temperature, not because it's exploding, not because you're reflecting light off of something else, not because it's undergoing some kind of chemical change, which gives you light, so it's not on fire. Well, it's on fire, but that's not what's giving you the light. You can't actually see the nuclear burning from the sun. What you see is the hot stuff that's on top of the nuclear burning. So we want to see how many photons come out of my object as a function of wavelength. And so we want to say that we're only looking at the temperature, so no reflected light, no scattered light, and it's in equilibrium. Those are the really important things, is you're only seeing the light that's coming from the temperature of the object. And this is distributed in a black body. So a black body looks like this. The beautiful thing about a black body is all the curves look the same, and they don't cross. So the black body is a family of curves that's parameterized only by temperature. And they're this nicely nested group of functions, and the peak decreases in wavelength as temperature goes up. So this is temperature 1, and this is temperature 2. That's much, much larger than temperature 1. So it's a family of curves that depends only on temperature. So back in the early 1900s, there was a question: why do we get this curve from my oven? So the whole question was, a bunch of dudes in France and Denmark had a bunch of ovens, and they would turn up the temperature and see how yellow they got. So they wanted to know why this oven that was hot is red and this oven that's really hot is yellow. Sounds like a really stupid question. Because of that, you have cell phones. Because of that, we have these incredible electric lights and communication. Because some dudes wanted to know why my oven is orange.
So, does the temperature at all depend on the material, or is it just the temperature?
Only depends on the temperature. That's it. Doesn't matter. Everything, when you're looking at the thermal radiation off of the thing, doesn't matter what it's made out of. when it's made, when you're looking at what it's made out of, that's line radiation. Talk about line radiation in a second, so you can see the effects of what something looks like by doing spectroscopy. This is only the temperature. And
How do we separate the two?
it's a complex process. So right now we're just talking about black bodies. So I have a black body in my lab. I just want to talk about that. As an astronomer, then you've got two different kinds of photons that you need to worry about. So we're going to look at a lot of spectra, which is flux. And really, like, the units on this are complicated, but just think about it as number of photons. Just think about it as number of photons per second. It's just an energy rate. I'm going to look at the flux versus wavelength. And if I have something that looks like this, that's line radiation, because it comes out in a very narrow peak. Or something that looks like that, that's line radiation that has a temperature, because it has some width. I'll explain the broadening in a second. But if it's pretty narrow, then it comes from a material process. But if it's broad, then it comes from a thermal process that doesn't have any discrete things. We'll talk about Kirchhoff's laws on Friday. He has these laws about what emits when. Basically, dense things make black bodies. In outer space, dense things make black bodies, and diffuse things make lines. So when we look at the sun, we're going to see the black body and lines because there's an atmosphere around the sun. So when they were developing this, they came up with these two approximations. Wien and Rayleigh and Jeans both came up with approximations that aren't really the right thing. But Planck realized that, well, okay, what we need to do is actually count how many photons actually fit in the box. And say, okay, I'm not going to have photons of any size. I'm not going to have an arbitrary number of photons of any size. That's the important thing. I don't get to have an arbitrary number of photons of any size. The number of photons that I have is quantized. That means it's not continuous anymore. That means it's broken into discrete integers. So the basic idea is like, how many of you play the guitar or some kind of instrument of some kind at all? Right. So, so when you play guitar, right, provided your guitar is in tune, you're only going to get one note when you pluck the open string. Right? You get one E or C if you like sludgy metal. So you get one note on this note. Because it's quantized. I can have, so let's say, I have a string, let's say it's 1 meter long. I can have a wave that's 2 meters long, that's half a wave. Or I can have a wave that's 2/3 of a meter long, but I can't have one that's 0.08 meters long because it doesn't fit, it doesn't make any sense. Because the guitar string can't move at the nut and it can't move at the bridge, so that every wave that I'm going to fit on my guitar string has to have a note at the nut and a note at the bridge. And then it can wiggle around plenty on the inside, but it can't do anything at once. It's quantized. So you can play this note or you can play a harmonic of that note. Yeah?
Is this why like the spin is in specific fractions?
The what?
Never mind. I'm thinking of something else.
Okay. I can talk more about it later, but I don't know what that is. I don't know what the start is, so we'll have to unpack that. So that'll take a second. Ask me that later. And an oven is the same way. I can't fit a photon of arbitrary length in this photon because it's got boundary conditions. And I can't fit a photon of arbitrary energy because I'll suddenly run out of energy. I can't have an infinite number of zero energy photons. That doesn't make any sense. So through all of that, and to really do that properly, you got to take statistical mechanics. So I think that you derive this in modern and you properly do it in statistical mechanics. And I'm not going to really get into the weeds there because otherwise it'll turn into a statistical mechanics class because I like statistical mechanics. So Planck realized that the proper, so they wanted to define this function b of lambda as a function of t. So this is the spectrum that I get as I vary the temperature, and it's a function of lambda. And so what they found was this. And Rayleigh could define this side pretty well, but his blew up. And Jeans could define this side very well, but but that doesn't cover everything either. It took Planck and the development of quantum mechanics to realize that B of t is actually, not going to write it down cold because I'll screw it up. The only thing I'm going to screw up is how many H's there should be. Do the thing. This is why I have notes. Two HC lambda to the fifth, no, lambda to the minus 5. Yeah, lambda to the minus 5 times e to the minus HC over lambda kt minus 1, and all of this to the minus 1. Let's unpack this for a second, and then I'll let you go. So there's two parts to think about. There's 2hc, numbers, I don't care about numbers, lambda to the minus 5. So when you go up that way, it decays with wavelength. And then it's divided by this gnarly thing, e to the minus e over kt minus 1. Let's talk about just this nugget for a second, and then I'll actually stop talking. E to the minus big E over kt. Now, okay, I wrote hc over lambda up here. What's the energy of a photon? Do you guys know? It's just some number h times its frequency nu. And this is one of the coolest things. That's it. That's the only thing that there is. So the energy of a photon is just h times its frequency. So that's equal to h nu, or hc over lambda, if you want to write it in wavelength instead. So up here I wrote hc over lambda kt. That's just e over kt. This thing is called the Boltzmann factor, and it shows up everywhere. What this says, in its core, as I say, I've got a thing that has some energy. I want to get to a certain energy. I have a certain amount of temperature. What's the likelihood for me to get to that energy? That likelihood is e to the minus e over kt. So if I have, say I've got two states that my state can be in. I can have an energy 1 and an energy 2. The probability of being in this upper level is just the energy difference divided by the temperature. You raise that to e to the minus that. So more energy difference means it's less likely to happen. This thing is key and will show up more and more, and you can see it's baked into the Planck function here. I'm going to stop talking now.
Oh, so this is why the black body radiation is like a distribution, kind of like a bell curve, but not really.
Yeah.
Because you can have different states, I guess.
Kinda. Well, really, just you have the most of the ones in the middle. So it's like, if I take my guitar and I sing at it.
Yeah, you have like the greatest harmonic in the middle, and then like subharmonics.
Yeah, I wouldn't think about it as harmonics and subharmonics when you get to the black body. It's not quite that simple. But it's an okay way to think about it, though.
I have a question about the second numerical 2.